Okay, so here I'm going to make a video for the two comparison tests. Should be pretty quick. Sorry, I don't have a fresh blank notes copy, so you're just going to have to deal with me scrolling through and talking through the filled out one, which should match what's on the website. So if you want to look at the website, you can fill it in there, and then you'll just hear my voice kind of just explaining it. But anyways, these two tests, pretty easy. Let's go through them. First of all, let's look at this inequality. See, I have some smaller series, a sub n, or a sub n would be the sequence, and then adding them all together is a series. So I have these two series, a and b, and let's just assume for now that a is the smaller one, and that b is the bigger one. Let's think about something logically. If for some reason, if I knew that the bigger series converged, so I know I could add all of those infinitely many terms together and it's some finite value. Well, if the bigger series is going to converge, is finite, that means also the smaller one is going to have to be finite as well. There's no way the bigger one could be finite, convergent, while the smaller one diverges. It just wouldn't make sense. Logically, we know that if the bigger one is finite, the smaller one must also be finite. Then we have this other statement. If I were to know that the smaller series, let's say a sub n, if the smaller series is divergent, means I can't add it all together and get some finite value, right? It's infinite, it diverges. If the smaller one is infinite, well then that's going to logically mandate that the bigger one must also be infinite. So that's what this test is really going to tell us. Whenever I have this logical inequality, I can sometimes get an answer pretty easily. So say if b of n converges, right? So if the summation of b, if the bigger series converges, is finite, then the smaller one must also converge. It must also be finite. Logically, that should make sense. And then we have the other statement that says if the smaller series diverges, is infinite, then the bigger series must also diverge. It must also be infinite. So those two work pretty easily, and they work pretty well. That's really great. Let's go through the first couple of examples. Basically, you're going to take your original given series and you're going to compare it. I don't know, it's kind of like the parent series, kind of like how you have parent functions. You're going to compare it basically to the easiest version of itself. So let's look through what I did for this first example. Here we go. We've got this first one, a. You've got the series 1 over n cubed plus 1. You're adding all those terms together, starting with n equals 1, then n equals 2, yada, yada, yada. What we're going to do, this is not geometrics. You can't use the geometric series test. That one's not going to diverge by the nth term test, because if you were to take the limit, it would be 0. So what we're going to do, right, is none of those other tests work. It's not a p-series, doesn't work. If that was not there, then we could use the p-series test. But nothing that we've done so far is going to conclude whether this series converges or diverges. So we're going to do the comparison test. And here we'll start with the direct comparison. So we're going to compare this to the easiest version of itself. Basically, just kind of ignore all those extra numbers. Let's compare this to 1 over n cubed, which we know, hey, this thing is a p-series. The p-value is 3. 3 is bigger than 1. So I know this new series, the thing I chose to compare it to, I know this is going to converge by the p-series test. Now that's great. Let's see if logically then we can now compare the two series. Remember, we had the original one, which is what we really want to know about, and then the one I chose to compare it to. We know that one converges, that one's finite. Let's see if that's going to dictate anything about the original series. Let's create an inequality. Okay, so let's compare the two. You don't really need the summation signs. Let's just look at the expression for the first one and compare it to the second one. We need to know, hopefully, which one's bigger and which one's smaller. If you look at the left, right, you have n cubed plus 1, and then the right denominator is just n cubed. Since this piece has a bigger denominator, n cubed plus 1 for sure is always going to be bigger than n cubed by itself. So since this term on the left, the original expression, since that term has a bigger denominator, you know that fraction as a whole is going to be smaller than this other one. So bigger denominator means smaller as a whole. So let's check. Here was my original. Here was the one I chose to compare it to. We had the inequality falling that way, which is really nice and easy for us to tell. We know that's going to be true no matter what n value you plug in. And remember, this new one that I chose to compare it to, we know it was convergent convergent by the p-series test. So this is finite. And if the bigger series is finite, it means the smaller one must also be finite. It was important that the inequality was facing this way. If it was opening the other direction, you wouldn't really know what's going to happen. But since I know the inequality faces like this, and I know the bigger one was convergent, was finite, I can logically conclude that my original series, the thing that you were actually trying to investigate, is also going to converge by the direct comparison test. All right, let's look at the next one. Here we go. We've got 1 over 3 to the n power plus 2. Again, that's nothing that we can use the geometric series test for. I can't use the telescoping test, nth term test, nothing like that is going to help us. Can't use the integral test, can't do it, right? So nothing that we've done so far will work. So let's try the comparison test. I'm going to compare it to 1 over 3 to the nth power again. You get to choose what you compare it to, but you want to make it something that's fairly similar to your original, because you're going to have to make this comparison and figure out which term is bigger and which one's smaller. So you basically kind of just ignore any of these extra numbers, compare it to the easiest version of itself, if you will. So here's the one I choose to compare it to. You could factor out the n exponent if you want. This is 1/3 to the nth power. This thing that I chose to compare it to, that's geometric. The ratio is 1/3, which is less than 1. And for a geometric with the ratio less than 1, I know it's going to converge by the geometric series test. So the thing I chose to compare it to is convergent. It's finite. Now let's look at the inequality. Remember, here was my original expression. Here is the one I chose to compare it to. Since that denominator is bigger on the left, I know this fraction on the left is smaller. So once again, we have this inequality falling very nicely for us. I know this is always bigger than this, and therefore, since this is finite, this other one must also be finite. And we can say, hey, therefore, my original series converges by the direct comparison test. It's very logic-based, very easy, I think, straightforward test, but it relies on that inequality facing the right way. I think we got 1 or maybe 2 more examples. Okay, so here I've got 1 over the square root of n minus 1. Again, nothing's going to work that we've done in the past, so let's compare it to the simplest version of itself, which you can rewrite as 1 over n to the 1/2 power. That's a p-series. The p-value is 1/2, which is less than 1. So since that's a p-series with the p-value less than 1, I know this, the thing I chose to compare it to, that's going to end up diverging by the p-series test. Let's compare the thing I chose to compare it with. Let's compare that and see how it relates to the original expression. Here, since it's the root of n minus 1, since that denominator is smaller, that means this term is going to be bigger. Or you can think about, hey, minus 1, this one, since it doesn't have any number, plus 0, this is the bigger denominator, so then this would be the smaller fraction. So overall, we get the inequality pointing to the right, opening to the left, which is opposite from what we got in the past. But that's okay. You need this inequality to end up falling this direction for this example. So I know this statement is true no matter what the n value is. My original expression is always going to be bigger to the one I chose to compare it to. And this one I know was divergent. That one was infinite. So since the smaller one was infinite, this other one, which I was really trying to investigate, this other one must also be infinite. So my original series diverges by the direct comparison test. It's a really easy logic-based test. Again, you get to choose what you compare it to, but at the end, you need to know what this inequality is going to fall out as, and it had better fall the right way. All right, I think that's it on this page. I just have some statements written at the bottom. Let's go through them. There's really 4 possible outcomes, right? Here we had the inequality kind of opening to the right for the first 2 examples. Here is opening to the left. There's really 4 ways this inequality could play out. 2 of them are good, the other 2 are not so good. So let's see. This test relies heavily on that inequality falling out one of the correct ways. So let's see. Smaller than finite must also be finite. That's what the statement 1 says at the very top. If you know the bigger one converges, then the smaller one must also converge. That logically makes sense. Also, larger than infinite must also be infinite. So if your smaller series is going to diverge, then that means your bigger one, 100% of the time, every single time, is also going to diverge. But if you know the bigger one is infinite, you don't really know anything about the smaller one. Or if the smaller one is finite, you don't really know what's going to happen with the bigger one. Let's think about something like this. So I just made up, again, just this inequality. If this is finite, 100%, you also know that A is finite. But if A is finite, you don't really know about B, right? If the smaller one is finite, the bigger one could be some larger finite number, or that bigger one could be infinity. You don't logically know anything if the smaller one converges. If the bigger one converges, 100%, the smaller one must also converge, but if that inequality is pointing the other way, you can't logically conclude anything. If the smaller one is infinite, if the smaller one diverges, then 100% the bigger one must also diverge. It must also be infinite. If the larger one, though, is infinite, you can't conclude anything definitive about the smaller. If this is infinity, maybe this is infinity minus 1, which would also diverge, or maybe it's infinity minus 10, which would also diverge, or maybe it's 5. You don't know. If the bigger one is infinite, you cannot logically conclude anything about the smaller. So that's what I kind of mean here. Two of the ways that the inequality could play out. Two of them are really nice. The other two are kind of indeterminate. You don't know logically what the answer is going to be. But this direct comparison test, it is very logic-based. I think it's pretty easy, but it relies on that inequality falling the right way. If that inequality points the wrong way and you can't logically conclude anything about your original, given the one you chose to compare it to, then you could move on to the next test, which is the limit comparison test. Let me flip it over, and we'll go through these pretty